Certain metals are either magnetic or magnets with their own magnetic field as a result of the arrangement of the atoms within it. This is a slow motion to build understanding of the domain theory of magnetics by Pierre Ernest Wise, 1906. When you put a magnet next to a book, nothing happens. There is no energy or force between the magnet and the book. When you put a magnet near some types of metal, iron, cobalt, nickel, or gadolinium, the magnet pulls the metal towards it. These metals are attracted to the magnet because of the arrangement of their atoms. We call these metals ferromagnets. One theory to describe the force of a magnet on a ferromagnet is the domain theory. The domain theory explains magnetic force with the concept that everything is made up of tiny atoms, a nucleus containing positively charged protons and neutrons and negatively charged electrons that whiz around the outside of it. Each of these atoms behaves like a tiny magnet. Whether or not the object is ferromagnetic, remember this means it is attracted to a magnet, or it is a magnet itself, is dependent upon the arrangement of the tiny magnets or atoms inside the material. One way of thinking about the domain theory of how a magnet works is imagine Magnet Public School. The school is made up of classes of children. Each child has a north face, it's north, and the back of its head, it's south, and so it behaves like a tiny magnet. In class, all these children face the same way, towards the front of their class. The other classes of children also face the front of their class, but in a different direction, and so the school comprises lots of classes, all facing different directions. The magnetic force of each class is cancelled out by another class facing a different direction. When the headmaster comes in, he demands that all the children in each class turn to face him. As all the children in every class turn their faces forward, all the classes align. The school has one combined force and so becomes one big magnet. So if we take a ferromagnet, like a needle, all the atoms in each domain are aligned, but each domain is randomly pointing in different directions. Along comes the external dominating force, a magnet. When we stroke the nail with the magnet repeatedly in the same direction, we are pulling the north poles of the tiny magnet atoms in the domains round to point in the same direction. When every domain is facing forward, the pin becomes a magnet. However, if we drop the new magnet or heat it to a high temperature, there is disruption to the alignment of the domains and the magnetization is lost. The domain theory also goes some way to explaining why like poles of a magnet repel and unlike poles attract each other. When domains of the magnet are all facing the front, with their energies pointing the same way, and a negative south pole approaches a positive north pole, the energies are aligned and attract each other. When the north pole force approaches another north pole force, then the two norths are facing opposite directions and fight against each other. The poles repel one another. So, in conclusion, a metal is attracted to a magnet, and so is a ferromagnet, because the atoms within each domain are aligned. A material becomes a magnet when all the domains in the ferromagnet are aligned. Opposite poles attract because all the domains are aligned. Like poles repel because, you guessed it, the domains are not aligned.